Hey guys, and welcome to another physics video. In this video I'm going to be starting a series of videos on thermodynamics, and some of this is going to be in the A-level physics revision series that I'm also currently doing on this channel. However, I'm also going to be doing a couple of videos that are beyond the scope of this syllabus. I thought I'd do a couple of extra videos on thermodynamics to join my university videos that are also on this channel. So in the first part of this series, I'm probably going to be covering the basics of thermodynamics, including things like what temperature is, the ideal gas law, the kinetic theory of gases. And in later videos, I'm going to be going into things like the laws of thermodynamics, the first and second law, entropy, all that kind of stuff, the Carnot cycle, and then getting into some statistical physics as well. But that's going to be a little bit later on. We're going to start off in this video looking at gases and the basics of temperature and heat and thermodynamics. So let's get started, and the first thing we're going to do, is we're going to define, oops, that was a rubber, we're going to define what we mean by temperature. So what is temperature? Well, in any sort of solid or liquid or gas, any sort of solid, liquid or gas is going to be composed of many different particles. These are the fundamental building blocks of any matter. It's all made out of individual atoms or molecules, but basically particles. And if you zoom in close enough, you'll find that these particles are actually moving around a little bit. They're not still, they're vibrating, they're jiggling, which means that there is, of course, energy associated with these particles. And what temperature is a measure of the kinetic energy which these particles have. As we'll see very soon, actually, the temperature and energy are actually directly related. But what temperature is basically the sort of movement, the jiggling about, the fundamental jiggling about of particles within any sort of substance. And to measure temperature, we need to use a temperature scale. The one that you're probably most familiar with is the Celsius or centigrade scale, which is of course defined in the range of 0 degrees being the melting point and 100 degrees C being the boiling point of water. This is. So 0 degrees is the melting point, 100 degrees is the boiling point of water. However, this temperature scale is not actually very thermodynamic. It actually depends on what the atmospheric pressure is, and we'll get into what pressure is in just a little while. But at atmospheric pressure, these are the temperatures of the melting and boiling points. However, these depend on the pressure. So if the pressure gets lower, then these temperatures, these values of the temperatures will actually change as a result. And so we actually need a scale which is not dependent on pressure. And this is where the Kelvin scale comes in. This is the Kelvin temperature scale. It's the SI measure of temperature, the Kelvin. And it has 2 points of interest. And the first point is 0 Kelvin, which you probably also know is minus 273.15 degrees Celsius. So to convert between Kelvin and Celsius, then you simply add on this factor here. So I can already say that the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. So rough example, if it's about room temperature 20 degrees, then that in Kelvin is simply 20 plus 273.15, which is 293.15. Now instead of writing degrees C like we do with the Celsius scale, we just simply write Kelvin. So there's no little degree symbol after the value of the temperature. That's just a convention. The first point on the Kelvin scale is 0 Kelvin. And you probably know that this is called absolute zero. So you're probably wondering what happens at absolute zero. Well, absolute zero is the point in which these molecules, which at any normal temperature will be moving around quite a lot, but at absolute zero, these molecules are motionless. They stop moving completely. There is no kinetic energy associated with the molecules at all. And so they're said to be completely still and hence at absolute zero. So that is kind of the definition of absolute zero. And also you can never actually get to absolute zero. It's only a theoretical value on the temperature scale. Experimentally, you can never get something quite as low as absolute zero. You can get pretty damn close. You can get a few billionths of a degree above absolute zero, but you can never quite get to absolute zero itself. So that's the first point on the temperature on the Kelvin scale. Now the next point is called the triple point of water, and this is 273.16 degrees. It's just slightly more than the other thing for some weird reason, and this is called the triple point of water. So what do we mean by the triple point of water? Well, we know water has 3 phases. It can either exist as a solid, which is ice, a liquid, which is the water which we all drink and kind of need quite a lot of, and as water vapor, which is of course a gas. So these are of course the 3 phases of matter. You probably already knew that. And normally you can never have all 3 of these existing at the same time. As we know, that these 2 can exist at 0 degrees C or 273.15 Kelvin, and these 2 can both exist at 100 degrees C or 373.15 Kelvin. But you can never have like the 3 of them all happening at once. So how do we get that? Well, as I said before, the pressure is actually also related to what phase the substance is in. And if you reduce the pressure from air pressure, which is quite high, standard atmospheric pressure is 1.013 times 10 to the 5 pascals. That is the standard atmospheric air pressure. If you reduce that value low enough, then there comes a point where you can have ice, water, and steam all coexisting at the same time. And that happens at 273.16 Kelvin and at an atmospheric pressure of 0.61 kilopascals, which you can see is quite a bit less than standard atmospheric pressure. So you've got to reduce the pressure quite sufficiently to get down to this point. But this is the point of ice, water, and steam all coexist at the same time. So let's just draw out our Kelvin temperature scale. So we start off at this point here, which is 0 Kelvin. This is absolute zero. And then you move up and then you get to 273.16 Kelvin, which is what we know as the melting point of water. This is actually called the triple point of water. It's how it's defined. And then if you want to get to the boiling point of water, then that'll be another 100 degrees up. So that's going to be 373 Kelvin. And this is the boiling point of water. So I'll also write in what it is in Celsius so that we know what we're talking about here. The triple point of water is actually 0.01 degrees C, which I know is a little bit weird that to have the 2 different things going on. But yeah, that's kind of how it works. And then you have the boiling point of water at 100 degrees C. So that is what the temperature scale that we're going to be using is. It's the Kelvin scale, and it's the standard temperature scale that us physicists like to use. So we're now going to start by considering gases. Now, what is a gas exactly? Well, gases are of course one of the three phases of matter. But what's happening in a gas exactly? Here are all our particles in the gas. But what's happening with this gas? Well, in a gas, all the particles are sort of moving around very quickly, very rapidly in all different directions. So unlike in a solid where they're all sort of dense and they're not moving around very much at all, in a gas they're all over the place. So they're all in random chaotic motion. They're bouncing all the way around, bouncing off different particles, bouncing against the wall of where the gas is in. And yeah, so you're probably wondering, how on earth do we start to even think about how to apply sort of maths to it? And this is, in a sense, one of the geniuses of thermodynamics, is that you can actually apply numbers to this what's seemingly quite a random thing. And it was about in sort of 1600, 1700 that scientists actually did start doing some experiments with gases. The starting point is that there are three laws of gases, and they are Boyle's law, Charles' law, and what's called the pressure law. It doesn't actually have a name, this one. It's just simply called the pressure law. And these laws concern three fundamental properties in which a gas can have. So let's just take a gas, which is inside a piston. Of course, a piston is just a container which contains a certain amount of gas. Here's the piston. Let's draw our gas out. These are the molecules of the gas. They're of course whizzing around, but of course they are stuck within this piston. And this gas, it has three properties at the moment, three fundamental properties. Well, actually four, but three more important ones at the moment. We'll come on to what the fourth one is in a sec. So this gas right here, of course, has a temperature, which we defined before. And we denote temperature with the symbol T. This gas also occupies a certain volume, which we give the symbol V, capital V for volume. And of course, this volume is exactly the same as the volume of the piston. So of course, gases expand to fill their volume, and therefore the volume of the gas is the same as the volume of the piston inside. And finally, we have the pressure of the gas, which is denoted lowercase p. And what the pressure is basically the force per unit area. And that's quite an important equation which we will be using later on. The pressure is the force per unit area. So the force of what exactly? Well, it's the force in which the gas molecules exert on the walls of the container. So of course the gas molecules are whizzing around in the piston. They could be doing all sorts of things, but of course they're going to exert some kind of a force on the walls of the container, and the force per unit area is the pressure P, and we'll see why we've defined it per unit area in a moment when we look at these three laws. So what are these three laws? Well, let's start off with Boyle's law. Now, Boyle's law states that the pressure of the gas is inversely proportional to the volume of the gas. The pressure is inversely proportional to the volume. However, this only holds on one condition. The temperature must be constant. So at constant temperature, the pressure is inversely proportional to the volume. I'll repeat that again though, that the temperature must remain constant. This law doesn't hold if the temperature changes. So if we plot out a graph of pressure versus volume, so we're going to put pressure on the y-axis, volume on the x-axis, then we'll get a simple inverse relation just like this. So the product of the pressure and the volume at any one point is a constant. So that's just another way of saying that they're inversely proportional. P times V is a constant, but only at constant temperature, and that's the key thing. It has to be at constant temperature. So that is Boyle's law, that the pressure is inversely proportional to the volume. We're now going to have a look at Charles' law. And Charles' law states that the volume is proportional to the temperature. And so that means that if the temperature increases, then the volume increases. And so let's do another graph of that to see what we mean. We're going to be plotting temperature in Kelvin, and we're going to be plotting volume, which is of course measured in meters cubed. So volume against temperature, what's it going to look like? Well, if it's simply proportional, then it's going to be a straight line. It's going to be a straight line graph. However, Charles's law also has a condition. Charles's law only applies if the pressure is constant, if P is constant. So therefore, like before, V over T, which is of course the gradient of this graph, is a constant, but only if the pressure is constant. So that is Charles' law. Volume is proportional to temperature, but only at constant pressure. And the final law is the pressure law, and you might be able to guess what this one is. It's going to regard pressure and temperature and keep volume constant. So, and that is exactly what it is. Pressure against temperature. What's it going to do? Well, it's going to be another straight line graph. The pressure is directly proportional to the temperature, but at constant volume. So at constant volume, the pressure is directly proportional to the temperature. And with both Charles's law and the pressure law, we can see that if the temperature is 0, then the volume is 0 and the pressure is also 0. They all hit the origin right here, which is a direct consequence of having temperature measured in Kelvin. If you have a temperature of 0 degrees Celsius, then that's still going to be 273 degrees Kelvin, and so there's still going to be lots of thermal energy, whereas if you measure it in Kelvin, you can see that you get a nice 0 point right here. So those are our 3 gas laws. We get that pressure is proportional to 1 over volume, which is Boyle's law. Charles' law says that volume is proportional to temperature, and the pressure law says that pressure is proportional to temperature. However, as you've noticed, all 3 of these laws require something to be kept constant. So now the question is, how are we going to combine these laws into something a bit more universal? And well, taking these 3 laws together, you get that the pressure multiplied by the volume divided by the temperature is an absolute constant. So you can vary pressure, volume and temperature of a certain gas, and this number here, PV divided by T, would always be a constant. However, it isn't quite a universal constant, because the constant actually depends on how much gas you actually have in the container. So let's draw out our piston yet again. If you're going to double the amount of gas in the container, then of course something's got to change. Either the volume will increase or the pressure of the gas will increase. So, something's going to have to give. And so therefore you can actually define a quantity which is little n, and n, if you remember from chemistry, is the number of moles in a gas. Now, moles can often be quite confusing, but the way that I understood it, certainly when I was learning chemistry, was just to simply think of moles like a dozen. So of course, a dozen simply means 12 of something. So say you have a dozen eggs, that means you have 12 eggs. So a dozen simply represents 12. But in the case of moles, then you use the word mole instead of dozen. And instead of 12, we're going to get a number much, much bigger than 12. It's actually 6.02 times 10 to the 23. and which is quite a big number, quite a bit bigger than 12. So 1 mole of something simply means that you have 600 hexillion of something. So if you sort of imagine a mole of donuts, then you would have 600 hexillion donuts, and that would probably mean you'd be rather large. But that is essentially what a mole is. It's just simply an amount of something. It's a certain amount. And this number right here, 6.02 times 10 to the 23, is called the Avogadro number. And what it does is it basically converts between number of moles of a gas to the number of molecules in the gas, which of course you can express mathematically as N, being the number of molecules in the gas, is equal to little n, which is the number of moles in the gas, multiplied by Na, which is the Avogadro number, which we often give the symbol of Na. So that is how you convert between moles and molecules. You simply multiply it by the Avogadro number Na. So if you have 1 mole of gas, then that simply means that you have 6.02 times 10 to the 23 molecules in the gas. It's slightly different from weight or mass. That's the thing that I think catches a lot of people out. The number of moles is not how heavy the gas is, it's simply the number of particles in the gas. Because of course how heavy something is dependent on fundamental properties like, sort of how many atoms are in each molecule. But, the amount is simply the number of molecules, which is slightly different to the mass of the gas. And incidentally, if you want to convert between the mass and the number of moles, then you simply have to multiply it by something called the molecular mass. So you have this quantity here, mR, which is the molecular mass of the molecule. And then you simply have to multiply that by the number of moles. So mass equals molecular mass times number of moles. And this mR here is dependent on what type of molecule is in the gas. So whether it's hydrogen or nitrogen or oxygen, then you simply use this formula here to do that. And this formula here is how you convert between number of molecules and the number of moles. So back to the PV over T equals a constant. You also have to take into account the number of moles in the gas. We're going to start off by just calling it moles. So PV over NT is what's called the absolute gas constant, the universal gas constant, which we give the symbol R. Now this R is a full, complete constant. It doesn't depend on PV, N or T. It's a pure fundamental constant of the universe, and it has a value of 8.314 joules per mole per Kelvin. You'll find that R has those units. And we can simply rearrange this formula to get the familiar ideal gas equation, which is PV equals nRT. And this right here, this, ladies and gentlemen, is the biggest equation pretty much in which we're going to be using a hell of a lot this video, probably a lot in the next video, and it's pretty much one of the cornerstones of thermodynamics. So if you're taking A level, learn this equation. You'll probably come across it if you do chemistry, in physics. You'll find this equation a lot. It's a pretty useful equation. You can actually also write this equation in a slightly different way. So what I said was that N, the number of moles, equals N, the number of molecules, divided by the Avogadro number, Na, which is 6.02 times 10 to the power of 23. So what we can do is we can substitute this into PV equals nRT. And instead of writing N, we're going to simply write N, capital N, which is the number of molecules, divided by the Avogadro number, Na. And we're going to multiply that by RT. Now, since R is a constant and Na is a constant, we can define a new constant which we shall call K, and K is called the Boltzmann constant, and K has a value of 1.381 times 10 to the minus 23 joules per Kelvin. And as you can see, it's a very small number. Often we put a little b right next to the K, so we actually call it KB, simply not to confuse it with things like wave number or spring constant or anything like that. So we normally just call it KB. So we can rewrite our ideal gas equation as PV equals capital N kBT. Often this form is a little bit more useful, I tend to find, because you don't have to worry about things like moles. Molecules, incidentally, have no units at all. They're just particles. They're not like sort of joules or volts or anything. They're just particles. So it is essentially a dimensionless quantity. So this is the other form of the ideal gas equation, PV equals capital N kBT.